So I'm going to talk about the cake pattern that we use in our team at KIXEYE. So, the cake pattern is, that's it. Okay, so the cake pattern, so what is it? Well, it's a software design pattern. It's used for dependency injection in Scala, and well, I also do a little bit of aspect-oriented programming, so you might not believe that, but I'll show a little bit of that. And it has no dependencies on anything, so there's no framework, nothing like Juice or such like. And it's type safe all the way, so you won't have any runtime things are missing or anything like that, for example. It was first explained by Martin Odersky and Jonas Bonér. Wrote a nice paper on the web, but actually there isn't that much on the web about the cake pattern, surprisingly, I think. So we've really had to learn a lot in actually using it in the real world to see what kind of ways we can use it. So I was trying to think, why is it called the cake? Well, I guess it's because it's got layers on it, like a cake. And if that's the way you want to look at it, then there's the interface layer, implementation layer, and the wiring layer, which is pretty much common actually to any dependency injection framework, right? So the top layer is the interface layer, or what I call component interface. So when you're setting up the cake pattern, you want to have a component which basically contains the piece that you want to inject. So that's the idea. So it's a kind of a trait inside a trait. So we've got, a interface for a vehicle, which doesn't contain much, and it's inside the vehicle component. So the vehicle component is just a container of what you want to inject into the application. And in this case, it's a VAL vehicle. But there are different ways in which we can use the component. So one of the important things about the component is that, about the cake pattern, is it's easy to get into a real mess. So what I've been trying to find in the last year or so is to find a way to use it in such a way that you don't get in a mess. And one of the ways to do that is to stick to a strict set of rules about how you're setting it up. So the first rule really is to have one access component per component. Sorry, one access point per component. So for instance, we're setting up a vehicle component. So what we don't want is multiple access points like capacity, shape. We want to make sure we just have one access point, the vehicle. And then define, or if you want to have multiple things in there, then you can define that with inside vehicle itself. Yep.
What led you to that conclusion? What problems did you encounter that led to that decision?
Well, I think if you don't do that, then you can quickly end up. Oh, repeat the question. Why did I come to that decision about one access point per component? I would say that if you try and not have that rule, then you end up with components that contain a lot of different pieces that need to be wired up, and it becomes very unclear and it becomes really messy. I mean, if you've only got a few components in your system, that's fine, but then if you've got a lot, you need to keep track somehow of what you've wired up and what you haven't wired up. So if you've got multiple access points, you could wire up some of them and not all of them. Whereas I keep a strict naming convention that allows us to keep track of what has been wired or not. And if there's just one thing to wire up, then it's easier to keep track of that.
So wouldn't that imply that you also have one trait inside, or multiple traits would have that same problem, right?
Right. Well, you just have just the one trait inside.
One trait.
Yeah. So and then we come to the implementation layer. So in the implementation layer, we want to keep track of a few things. Firstly, we want to keep track of is, well, we want to implement it first. So here we've got a car, which is extending vehicle. So car is our implementation of vehicle. And in a car, we want to do things that are specific for a car, such as, keep track of its fuel, keep track of the road. So they would then end up being dependencies. So that's where another useful thing that I found is to keep a companion class to keep track of the dependencies for your implementations. So here we've got a car component, object, and we have a type alias called dependencies, which shows that we depend on, so a car depends on a fuel and the road. And then in the actual trait here, sorry, in the actual trait car component, which is extending the vehicle component, we can actually just use in the self type, we can just refer back to the dependencies there. So we don't have to, this really avoids having to repeat the list of dependencies, especially as they go down the stack of dependencies. And then if you change one somewhere along the stack, it can break everything because you've got to change that all the way in other places. So you kind of become dependent on your dependencies. So in this case, just note in the car implementation, we're actually calling the hash. That hash is just a hash code for. It's nothing fancy. It's just calling a function on fuel and road when we create the car. So just remember that because I'll come back to that later. And then the third layer is the wiring up. So the wiring up is where we actually wire up the actual car and say that it's got to be a new car. So now in this case, in our component, we did var vehicle. I think I made a mistake there. I've been through this so many times. It should be a lazy val vehicle equals new car there. Okay, so because we're specifying the actual implementation of vehicle there, and the lazy there is because when we wire up all these components, there's no guarantee in which order the vals are going to be wired up. So if we put lazy there, that avoids having to think about the order in which things are wired up, and it will guarantee we won't get any null pointer exception. So, and then we come to, modules, how you bring together all this wiring into your big wiring for the application. So you might layer this, and so I might have an intermediate sort of multi-component wiring. So here we, actually let's just go back a slide. You notice here I've changed the naming convention, so we call car wiring extends car components. So that way, if we see anything called wiring at the end, we know that it's already been wired, whereas if it says component at the end, we know that it is yet to be wired up. There is no wiring yet. So when we've got multiple component wiring, we're really just bringing together different wirings or components together. So in this case, a transport wiring is dependent on the car wiring, a diesel component, and a highway component. So because it says diesel component, we know that it hasn't been wired. So that means at the bottom here, we have to actually specify that the fuel is the new diesel and the road is the highway. Otherwise, it's not going to be wired up. And I would be lying when I'm saying it's transport wiring, because it has to be fully wired up. So it's really important to keep to these kind of conventions, because another reason is because the various IDEs like IntelliJ, when you don't wire it up right, it doesn't come up with very useful errors. So you need some discipline in doing this. So what is wiring? So it's important to keep the difference between the wiring and the component. So the component, we should not have wiring in a component. So if we see a component, it's not wired. So wiring is actual, think of wiring as configuration. Think of it as like your XML configuration in Spring. Okay, so it's programmatic configuration. So we're trying to keep the wiring separate from the actual implementation as much as possible. And finally, application wiring. So this is where finally we have a class as opposed to a trait right at the top, so we can actually instantiate it. So if this compiles, that means we have fully wired the whole application. So in your top class in the system may have a whole long list of all the things you want to wire together. And so each of these, like transport wiring, home wiring, office wiring, they may be just kind of modules of sub-wiring that you're putting together. So you might have all your database wiring in one place, all your event bus wiring in another place, and you want to bring it all together finally in the application wiring. So, mixing the cake. So I mentioned earlier on that we got 3 layers, the interface, implementation, and the wiring. We can actually flatten this cake a little bit. So in the top row, we've got the full cake. So we've got the interface component, and then we've got an implementation component, and then finally we've got the wiring. So just to remind you, so in the interface component, it's basically a trait inside a trait with a val, which is your access point. It's kind of pseudo Scala code. Obviously, that's not real. And then the next one, we've got the self type, which represents the dependencies in your implementation, presuming that they do. And then the class, because you're actually implementing the trait that was in the interface. And finally, on the right-hand side, you're actually telling what the val is, so that's the wiring. So we can actually take any 2 of these, so the left 2 or the right 2, and we can actually collapse them in so that we just end up with a cake that's 2 layers. So in the first case, we're just going with keeping the interface component free, and then we're actually doing the implementation and the wiring all in one. And the convention that we found very useful is to call that a wired class. So the distinction being that wired has implementation and wiring all together. Now, that may not sound like a good idea, but it's actually very useful, and you don't really lose anything because at the end of the day, you can still mock the original interface component or replace it with a different implementation. Because usually the wiring for a single component is usually pretty trivial. And the last case is where we're actually bringing together the first 2. So, maybe there isn't any kind of interface and implementation layer. It's all just the class straight off. But we still want to be able to mock it or put in different things. So we need to leave the wiring out of that particular case. Because if we collapse it all down to a 1 layer, then it's not really dependency injection anymore. So just to reiterate that, so wired is basically implementation plus wiring together. So in that case, we must extend the component interface, right, to give us the wired. And we've got to do both the wiring and the implementation together, all in one place. And the wiring is usually so trivial that you're just instantiating the class, for example, in this case. Now, for the component interface, I've only really mentioned that we can have a val, but there are actually lots of different options, and I was anticipating that. But before I go into that, so say you want to you want to test these components you built. So, let's take the car wiring, for instance. We know that depends on fuel and road. So if we want to wire it up, we need to effectively make like an application. So we're making a test application, or what's called class test wiring. So that needs to fully compile. So we've got car wiring, so we know that's wired. And then we've got fuel component and road component. So we know they're not wired, and we want to mock those. So we're just going to fix them in with a mock of the fuel and a mock of the road. And then when we test it, we just instantiate new wiring. We just so if we call the hash code on car, that means because it was a lazy val, it's then going to be instantiated. It's then going to fire off and call fuel and road hash inside that class, and therefore we're just verifying using Makito. So I like Makito because you can mock anything, even fully implemented classes. And scoping. So, I've showed you really the first case, which is singleton scope. So you just want to put one instance of a planet or something, and you want to inject that into your system. But what if you want to do different kind of injections? So traditionally, that would be called scope. So, and all I've shown you so far is singleton scope. So let's say we have no scope. Well, that's just you change the val to a def, and then you basically get a new instance every time you make a reference to it. And usually, or sometimes you want something which is a little bit in between, some kind of managed scope. So there are a few different ways of doing this, but one way to do it is like this. So we just have a trait which says with connection component, and then every time you call with connection, you're going to manage that. So you're going to create an instance of connection, and then after that function has been, that block or block of code, the function has been called, it then can close off the connection automatically. So it's nice to, so it doesn't put any responsibility on the caller to make sure the connection's closed. You're carefully managing the scope of connection. So that's pretty handy. So I've used that in all sorts of places, like, you know, RabbitMQ, event bus connections, etc. Another possibility is something called a context scope. So here, you know, we can actually have, so in the so like the service component here, so the access point is service, but we could actually have arguments that it takes. So in this case, we're doing context, and we're making implicit. So you know, context. So we've kind of got implicit injection and cake pattern mixed together here, but it works. It works very well. So in this case, maybe we've got some kind of health service, and as you see on the bottom, this is fully wired because we've got the wiring. So we're saying that service implicit context is equal to the new health service, and the health service, when it's instantiated, will automatically get the context will be injected in at that second point as well. So this is a good way of, you know, putting in the context of some kind of web call, for example, like, you know, the session, if you like, you know, the username or any kind of context related to that. And then I mentioned aspect-oriented programming at the beginning. So this is another good, you know, good example, I think. So we definitely use this. So this is a way of controlling transactions, for instance, on a database. So we can have a transactional component, and then in there we've got the transactional, and then we want this function to return any type, however you happen to be using it, and we're passing in a block of code. So this is like a DSL, domain-specific language, or it's like, well, it's call by name, and effectively extends the grammar of Scala. So you can do some really funky things. So if you look at the cake pattern usage, it's basically saying that in this add function, we want to add 1 and 2, and we want to make sure that that's a transactional thing. That probably doesn't mean anything there, but if it was doing something with a database, then you could make that a database transaction, for example. Yeah?
Does the pattern allow you to compose multiple transactional blocks? So for example, you have def add equals transactional equals 2. If you had a similar thing like def subtract equals transactional equals 2.
You mean like, so you've got one method which is transactional and then it calls another method that's
well, so
got...
you have 2 methods that are transactional and then you want to make a third that's a proposition.
Okay, right. So the question is, what happens if you've got, you know, multiple transactionals? So in other words, you'd have something like in transaction, for example. Yeah, I mean, we do that. So we actually use Slick, which is a really great ORM, recommend that. And so, and one of the ways you can use it is effectively putting the transaction state on thread local. So when you actually implement this transactional component, you can say, well, am I already in a transaction? Pick it up from thread local. And if I am, then I'll just reuse that. So that's how we do it. And then if you compare that to the way you do that in Spring, or one way to do it, I mean the one that compares, so you could just annotate it in Spring and just say at transactional on your method, and it will somehow weave in some magic. So it almost looks the same, except we haven't really got that much magic other than Scala magic of the language. So, you know, you could argue maybe that isn't fully AOP, since, you know, I have to actually, if you like, annotate it with transactional here. I can't just leave it completely empty and somehow I'm going to weave it in externally. But it's pretty close, and you know, and it's pretty unobtrusive. So, and when you're doing tests, of course, you can just have an implementation of transactional component that basically does nothing, just lets it pass through. A kind of no transactional wiring component. So don't eat too much cake. Now the problem with the cake pattern, another problem is that you can really get carried away, and you can end up with having components for everything and things that shouldn't be in components. So one way to break out of that kind of never-ending tree is to actually not necessarily define traits inside traits, and to actually, so if things are relatively simple objects, like a clock, for example, don't define that necessarily within a clock component. So here you can see, for example, that I've got a trait for clock, and I've got an implementation which is called system clock, and then I've actually built a clock component which holds a way in which I can inject the clock, but I haven't defined clock inside the clock component. So, and sometimes that is pretty useful, especially for the simpler objects in the system. And probably necessary, so especially if you want to inject things that are externally defined somewhere else, then you can't obviously put it inside your trait component. Yeah. Okay. Implicit sub-injection. So you noticed on the last one that I've actually got an implicit on the val, so you can play all sorts of games there. So it's got a cake pattern, but I've got an implicit val, not just a val. And so that means that we can, so for instance, we've got a ticket case class, and in there we've got a purchase time on it, and when we instantiate it, we want it to pick up the time from the clock there. So now if we define clock inside a component, then suddenly we would have to have the ticket case class would have to be inside another component, and then it goes on and on forever. So, but this way, because clock is defined, it's a relatively simple object, doesn't need to be encapsulated in a component. I mean, the only reason to keep it in a component really in the first place is so that you're forcing people to use that particular object within the cake pattern for a good reason. But in this case, there isn't a good reason. So here you can see how we've made the cinema component depend on the clock component, and because it was an implicit clock, it's automatically got set up into the ticket. When we buy a ticket, we do the ticket film, and it's picking up the implicit clock and reading the time. So, people complain about implicits because you can really get carried away with invisible things, but so you've got to keep it to moderation, things that really are universal through your application. Obviously, your whole application is probably interested in a clock. Your whole application may be interested in an Akka system, for example, or an execution context. These are the things that are useful to have as implicit, but you certainly don't want to get carried away. Setup and tear down. So when you're wiring in things like databases or event buses or anything that involves, or even a web server like Soccer, then once the whole thing's been wired together, you need some kind of way in which you want to set everything up and tear it down. And we never really found a way to do that was pure cake. So it lies as a bit of an exception outside of the cake pattern, but this is as close to cake-like as we were able to get it. So we've got a setup hook component. So it's a setup hook component, and it's got an access point called setup hook. So that's good. But it takes a method, which is essentially a call by name. So that's a piece of code. So that's the piece of code you want to do when you set up. And there's the actual setup hook wired. So remember, that's the implementation plus the wiring all in one. So and the way this falls down a little bit in the cake pattern is it actually has got another setup method there. So it's actually got two access points in a way. But at least the second access point, i.e. the actual setup function, at least that's not accessible from the original trait. So it's only really accessible when the whole thing has been set up, which is actually a good thing because you don't want people calling setup anywhere else except when the whole thing has been put together. So I'll show an example of how the setup hook is used in a couple of slides. So actors are a bit strange in many ways in Scala because we all like statically typed and type safety, but actually actors, or the actors that we use most of the time, are actually not really typed at all. So it makes using the cake pattern with actors is a little bit tricky. So also within the one of the things in the actor systems it says is you're trying to find out how you're supposed to use dependency injection with actors. The literature on the web is pretty unhelpful and probably inconsistent as well. So this was probably the best that we could come up with. So it's a little bit around in circles because I don't want to put the echo actor, in this case, into an actual component. So I don't want to put it into an echo actor component. So the only way to inject things is to actually have a concept of injector. So this is beginning to look a little bit like structured type dependency injection. I don't know if you've ever looked at that. It's not quite there, but so we can see we've got the injector. So we want to pass in anything in there which implements that, which at the top, the echo actor dependencies is the listen component. So we've got this echo actor that basically what we wanted to do is any message you throw at it, it's going to reply the same message, and it's going to call the hash code function on the actual listen thing that it's dependent on. So that's what it does. You can see this extends actor, and in the receive method, it's got a case match where it's matching any message that comes in, any message of type message, and then it's calling the hash on the injector.listen.hash, and then it's replying the message back to the sender. So actually just go back to that. So try and remember that because I'm going to show how to test that later on. And so we've got props wiring. So this is the thing about the types. So we want to have a props for the echo actor. And as you can see, it's of type props. So really you can put anything you like there. It's not really very tightly coupled there in terms of dependencies. But that's actually pretty useful because that means when you're mocking it, you can put anything in there, such as the test probes and stuff that come with Akka testing. So if you hadn't noticed, we use Akka quite a lot at KIXEYE, and it's super fast and really, really nice. So in the Akka props wiring here, so we're extending the Akka props component, we are actually doing the wiring, as it says. So in the wiring, it's just props new actor self. So this is actually not the recommended way of starting an actor, but it's the best one I find because it means that it's actually checking to make sure that the types all tie up. Because if you do it a different way, i.e. props class of echo actor comma self or whatever, then even if you get the types all wrong, it will still compile, and that's not great. So, and I think there's some flux in the Akka development as to which way this is going to go in the future anyway. So, and arguably you could say this is some implementation going on here, but the props new echo actor self, it's not just new something, is it? There's something a little bit extra there. But usually in our code, if it's just a one-liner and it's pretty simple, we turn a blind eye and say that's wiring. So I just want to show you, so bringing a lot of things together here. So we've got, Akka. We want to test this actor called the echo actor. So we're going to use Scala test. We like that. We like Nikito. and we like Akka test kit. So it's all kind of in one. This was a bit of a challenge to get it. I hope, yeah, you probably need to come closer if you're further than halfway to see this. But so you can see an echo actor so I'm using word spec, which is my favorite spec, so that's a bit like specs 2, which I used to use before using Scala test. And it gives this kind of behavior-driven development type of feel to it. And I'm using matches and Mikito sugar. So an echo actor should echo a message. So the first thing I do is set up the actor system using test kit. And you can see that I shut it down at the end. This is just to try and get it all in one page. So it's probably not the perfect way to write this, but it shows all the different pieces. So we can see that we've set up the actor system and we've extended that with echo props wiring and listen component. So you can see that wiring means it's already wired, so we're finished there. And the listen component, that's a component, so we need to wire that. So the first thing I do is set up val listen equals mock listen. So we want to create a mock for that because we don't want to use a real implementation. We create a message because we want to chuck a message at the echo actor. And then we're going to actually, all we've got actually here is the echo prop, so we don't actually have an actor. So we're going to fire up an actor using system.actorOf. And then we're going to use test probes, so they're a really useful part of Akka where you can sort of emulate sort of actors. So the test probe is a bit like your own kind of test actor. And then we're going to send a message. So akka.tell. So the reason why we're using tell as opposed to the exclamation mark, which you may be more familiar with, is because you want to specify where it's coming from. So I want to say, although I'm sending the message to the actor, and I'm sending that message, I want to make it look as if the probe sent it. So that way, I expect the reply is going to come back to the probe. So that's why the next line I'm saying probe, I expect the message. That's the message I expect back to replied. And then inside this actor, it should be kind of pinging the listen component with the hash function. So we're just verifying, so using Mikito to verify that that method's been called. So you got through that. So, and finally, actor wiring. So I did the props and how to wire that. So how do you wire up an actual actor? So when you think about it, there's quite a lot going on with an actor. So I need to have the props. I need an actor factory ref. So an actor factory ref is either the whole actor system or it's an actual context of an actor. They both implement the same thing. So, so this is a more generalized kind of component. And then I'm also using the setup hook component. So this is where I promised I was going to use it. So if we look down here, so it's echo actor wiring at the bottom. So we're doing wiring. So we're saying lazy val echo actor equals, and then we're basically instantiating the actor. But remember, this is lazy. So when this has all been instantiated, this actor still won't be running. So the only way to get it running is to actually do something on that reference. So I'm just doing dot hash code. So it's my kind of way of touching or pinging the lazy val. So that's what the setup hook will do. So when the whole thing's been wired up and started up and somebody calls setup, then it will go through all the different blocks there and it will basically start that actor going. And why there? Because some of the dependencies that actor has may not have been set up by the time that particular val has been instantiated. So it's just erring on caution because you don't know the order in which things are wired up. And getting near the end here. So yeah, I've been through quite a lot of things and with the cake pattern and really talking about the conventions that we've sort of evolved to. And so, you might, I don't know how many of you are using the cake pattern. So how many people are using the cake pattern in their company at the moment? So, okay, not that many. So, I mean, a cake pattern obviously has some detractors. So the main one being that it's got a lot of boilerplate. And I probably agree with that. But it does have a lot of flexibility in the way that you can actually do it, as long as you stick to some rules, because it can lead to a lot of chaos. But I think there might be some hope in the future to reduce the boilerplate. You know, I've been trying to think about how to do that. Maybe somebody else can think of a way of, you know, using some of the macros in Scala 2.11. So, you know, we had that talk a couple of weeks ago on Mac wire, so that was obviously an interesting variation called the thin cake. You know, but which I like that, but I still think there is something undiscovered here. So anyway, let's just go through the conventions that we've kind of narrowed in on. So the first one is the one I mentioned in the beginning, which is like have one access point per component. You know, I find that keep some of the complexity down, although it does increase the number of classes. So that's kind of the downside there. But at least you kind of know where you are. And then I stick to this strict set of suffices for the classes, so like component, wiring, and wired. So with wiring and wired, you know that everything's been wired, so it really helps keeping track of what's been wired and what hasn't. And the type aliases for dependencies, I haven't seen that anywhere, so we kind of invented that one. So, but that's really turned out to be really helpful when you've got a lot of things being injected in. You know, it means that you know, these lists of arbitrary dependencies in certain places, you know, you say, well, it doesn't really depend on there, so it becomes very, very coupled as it goes up and down the stack. So that really helped. And the last one is to have at least 2 layers in the cake. Well, that's kind of obvious, because otherwise you're really cheating, and you know, there's no way. It's not really dependency injection anymore. It's all just put together. So why have all these conventions? Well, it makes it work effectively in a team. You know, if working with a team of people, if you have some rules about how the cake pattern is done, it really helps. I mean, if you're just on your own, it probably is okay, but once you're beyond a few people, then it really helps. And you keeps track of the wiring problems. So, you know, really the IntelliJ and presumably Eclipse too, although I haven't tried it, has real trouble finding out where if some kind of wiring goes on. I mean, the beauty of the cake pattern is that if it doesn't compile, you haven't finished, right? It's not going to run, as opposed to other dependency frameworks, which may compile and it may, but it's only a runtime that you find it tells you that something's missing. Here, if it compiles, you know you're there, but unfortunately, if it doesn't compile, the errors can be very, very obtuse. So it really helps to have some conventions. And it's easier to extend and rewire. I mean, these kind of obvious benefits, I think, but they do really help. And that's it. So KIXEYE, we make, as we said earlier, make computer games, and I'm part of the shared game services where we create services. We create any service which is used by at least one game. That's our kind of remit. Any questions?
So I assume you don't use Spring dependency injection, or in other words, if these dependency injection, you know, ways that you've shown are sufficient for your needs on dependency injection.
So the question is this sufficient for our needs, and do we use Spring? This is all we use for our dependency injection. There are lots of different teams at KIXEYE. It's a lot of people working here. So, you know, there are teams that are using Spring. And in fact, I've used Spring myself in the past. I've used Juice, and I prefer Juice to Spring. I've used Subcut, which is a Scala dependency injection framework. That's not bad. MacWire looks good. But I haven't used that yet. That's pretty new. What else? I mean, if I abandoned Cake, I'd probably go for Juice at the moment. Any other questions?
Sorry, so I might have missed it, but is the class at the top that extends your components, is it its responsibility to call the setup for your setup hook?
Yeah.
It will iterate through and pull all the setup hooks that you, or other components that you mixed in and purchased.
Yeah, absolutely. So your top application wiring here, so this would typically open, it would run setup as the final thing once everything's been set up. Yeah. And here, so this would be with office wiring, and then it would see with setup, hooks, wired. If we go back to that. Yeah, so with setup, hook, wired. And there's a similar one for teardown. So as you can see there, it basically iterates through, so it keeps track of all the setup hooks that all the different components are put in there. And right at the end, you click setup, and it will go through them all in no particular order in this particular case. So you might want to embellish that. We actually have a version where you can specify some kind of number about ordering. So I like default is 0, and then if you put -1, that'll be done first, and if you +1, it'll be done last. So you can embellish this. I was just giving the kind of simplest case scenario.
So you mentioned this problem that one of the big problems we have with Cake is really, really poor error messages when something is wrong with wiring. Which, like you mentioned the conventions that help you kind of with that. Which one is it? The time releases, or what really helps with that?
Right. Okay. Yeah. So he's asking a question about how do we track down wiring problems in the Cake, and which feature is particularly helpful. Yeah, I found the dependency having the dependencies listed really helps, because you can, if you're really stuck, you can just copy and paste those in up the stack until the actual, and you can keep on going down until it actually highlights the one that's actually responsible for it not wiring up. I don't know if that makes sense, but it does. Yeah, it's difficult for me to show that in a talk. But yeah, I would say the type aliases is probably the number one thing that helps. But definitely having this convention of wired and component, or comparing component with wired and wiring, that was probably the second most useful thing in terms of controlling that wiring difficulty, tracking down wiring problems. Any other questions? Okay. Well, thank you. Carry on having some food, and as say the KIXEYE are hiring, and talk to me afterwards. Okay.